Professor Roman, my name is Yafang Zhang, and today I'm going to present in my microeconomic forecasting for U.S. product supply of crude oil and petroleum products. This data time series is from January 1981 to December 2022. So let's start it. This presentation going to have two parts. The first part is time series description. From this graph, we can see a general upward trend from the early 1980s to 2005, indicating growth. A slowdown and plateau between 2005 and 2010. Uh, Most importantly, there is a sharp decline around 2020, likely due to external economic shocks such as COVID-19 pandemic. Additionally, by analyzing 1 year dynamics, February exhibits the lowest values, while August tend to have peaks. This suggests that seasonality plays a crucial role in our analysis. Then let's look to the seasonalities. The data exhibit the data shows strong seasonalities with constant peaks and soared in each years. The mean values suggest a certain month have the higher values such as January, July, and August, while February, April, and September seem to have like lower values. To better understand the nature of our time series, we perform descriptive statistical analysis. So from this graph, we can see mean is equal 563,722, and we also see the maximum, minimum, but the most important that is probability that is really is very slow, meaning we reject none. A time series must be stationary before applying ARMA models. So from the ACF graph, have us determine whether the time series is not stationary. The ACF shows a slowly decline over logs. The PACF shows significant spikes at log 1 and log 2 before cutting off. This suggests a strong autoregressive structure because PSF have sharp declines. A moving average component may also be present as the ACF doesn't drop off immediately. The high auto correlation at log 1 in ACF suggests non-stationarity, so the ADF test should be conducted. So we then conducted the ADF test to check for stationarity. We use the first model that is constant only. From the output, we see the probability that is over 0.05. There is at least one UR in 1.5, meaning that is non-stationary. After applying first differencing, the series become stationary because we reject the none. There is exactly one UR in 1.5. Secondly, we use model 2 that is trained and constant. We see the same results. First, we reject none. There is at least one UR in 1.5. Then we apply for first differencing. We reject none. There is exactly one UR in 1.5. Finally, we use model 3, which is non-variables. There's a same result from the output. We can see from here and here. Final conclusion, there is one UR in 1.5. We need to work with first differencing. There is a graph of dy5. From that, we know dy5 is stationary, making it suitable for a Riemann forecasting. This is the second part forecasting. We divided the period on training period, testing period, and real forecasting period. To select the best forecasting model, we compare 20 different ARIMA models based on AIC and RMSE. The best performing model based on AIC is Serama 3-4, and the AIC value equal 22.587. And from AIC, we can see the top 20 models from this graph. We pick up like top 10 ARIMA models for DY5, that is over here. However, when we use RMSE for model validation, the Serama model 2.5 was found to have the lowest RMSE, making the best model to forecasting. Then we use this best model to estimate it based on all data. We can see the key findings. The AR1 and AR2 were highly significant, suggesting strong dependence on past values. The MA terms were largely insignificant, implying that the model meaning relies on auto-regressive components. Oh, so we use this best model Sorama to for we forecast 12 months in ahead in from January 2023 to December 2023. There is the output, the green line in the forecast graph presents predicted values. The blue line indicates different intervals. The forecast significantly captures the seasonality with product with product values oscillating in patterns similar to historical fluctuations. To summarize, the Y5 time series shows both long-term trend and strong seasonal patterns. Strong seasonalities and seasonality analysis show that differencing was necessary for accurate modeling. The Surama 2.5 model was chosen as the best fit based on RMSE. The 12-month focus for 2023 indicates stable projections with seasonal variations. So that is all my presentation. Thanks for watching.